today we'll look at actual examples of torsion problems. So the first example that I will consider is an elliptical cross section. Square by a square plus y square by b square equal to 1. So this is the equation of the boundary of the ellipse. And so let us try to find the warping function, the conjugate function, and this Prandtl stress function. Right? These are the three functions to be found for this particular problem here. So actually, in this case, it turns out that the easiest function to find is the Prandtl stress function. So what we do is that we will guess phi as equal to m times x square by a square plus y square by b square minus 1. See, the thing is here that in this particular case we know that phi should be equal to 0 on the boundary, and then inside this domain we have the equation that del square phi is equal to minus 2g alpha. Right? So we'll write this equation of the boundary itself, because we can directly see that this phi will vanish on the boundary. So this m is a constant that is to be determined now by using the governing differential equation. So if you substitute this into the governing differential equation, then what we will get is that del square phi is equal to minus 2g alpha will lead us to m is equal to minus g alpha times a square b square divided by a square plus b square. Okay? So, but one important thing to note here is that this kind of a technique will not always work. So that means, suppose we will take the example for rectangular cross section. So we cannot simply multiply the equation of the boundary by a constant and get the governing equation to be satisfied. Okay, so so it works in certain cases, but not in all cases. So in this particular case, it works, and so we find the solution using this particular method here. So if you substitute this value of m, then what we will get is that minus g alpha a square b square divided by a square plus b square times x square by a square plus y square by b square minus 1. So this is the Prandtl stress function, and the non-zero stress components associated with this Prandtl stress function are now xz is equal to minus 2g alpha times a square y divided by a square plus b square, and now yz is equal to 2g times alpha times b square x divided by a square plus b square. Okay. And then from this we will get that the shearing stress, we had talked about this shearing stress in the last class. So that is equal to tau xz square plus tau yz square. That is equal to 4 times g square times a square divided by a square plus b square square times a raised to 4 times y square plus b raised to 4 times x square. And we want to find out where the maximum shearing stress occurs. So we know that the maximum shearing stress occurs on the boundary. So that we proved in the last class. So let us now use that particular information to find out where the maximum shearing stress occurs here. So to find T max, use the fact that occurs on the boundary C, right? This is the boundary, so it occurs on C. So you basically substitute y square is equal to b square into 1 minus x square by a square into this particular equation, which is star. So let us call this as star. So into star. Okay. So you'll get that. So on C, you'll get that t square is equal to 4g square alpha square divided by a square plus b square times a square b square minus x square b square times a square minus b square. So this is the expression that you get. And from this you will see that the maximum, okay, will always occur for x equal to 0. Because so since a is greater than b, so this a square minus b square is a positive term, b square is also a positive term, right? And so the maximum will occur at x equal to 0. Let us write that here. So this so since a square is greater than or equal to b, t square is maximum when x is equal to 0. Okay, so and y is equal to plus minus b. And so basically these are the points. So if you draw this, these are the points where the maximum shear stress occurs. And this is something I mentioned in the last class, that according to our intuition, actually we may think that the farther away you go from the axis of torsion, the more will be the shear stress. But that is not what happens. So here you can see that actually the maximum shear stress occurs at the end points of the minor axis and not at the end points of the major axis, as we would expect from our intuition. So this is a very, very good example to show that intuition does not always work. And so you have to have a mathematical analysis of any problem, and as you can see from this particular problem here. And so your T max now, so T max, it turns out to be 2g alpha a square b divided by a square plus b square. So this is the final result here. So this is at the extremities of the minor axis, right, of the minor axis. Yeah. So this is very, very important here. Okay. Then we can find out what is the torsional rigidity also. So let us find that. So torsional rigidity is also very important, right? Because that gives a measure of how much angular deflection will occur for a given torque, right? And we want the angular deflection to be small, right, for a given torque. So we will always design our cross section so that this torsional rigidity is more, right? So that is why finding this torsional rigidity is very important. So we can use this formula that either you can use this x times tau yz minus y times tau xz formula, or you can use 2 times phi, integral of 2 times phi, because this is a simply connected region. So you can use that formula also. So we derived that, right? Last time in the last class we derived this particular formula, that t is equal to this. So with either formula, what you will get is that 2g alpha divided by a square plus b square times integral of b square x square plus a square y square times dA. This is over a, and we need to now evaluate this integral. So this integral is very easily evaluated by making a substitution. So what we can substitute is x is equal to ar cos theta, and y is equal to br sin theta. If you make this substitution, actually one can evaluate this integral quite easily here. So so we need this dA. Okay, so for that we need to find out what is the determinant of the Jacobian matrix. So I'll just show you how to do that. So the Jacobian matrix is del x by del r, del x by del theta, del y by del r, del y by del theta, and the determinant of this, so determinant of this will be equal to a b r times, so you will get that dA is equal to a b r dr d theta. Okay, so using this Jacobian, this is what we will get. And so let us now evaluate this particular integral here. So this will be equal to 2 times g alpha divided by a square plus b square. This is integral from 0 to 2 pi, and then this is integral from 0 to 1. Then this is a square b square r square times a b r dr d theta. So you can see that now the integration limits are fixed. So if you had tried to do this integration with respect to x and y, then the limits of integration would have been variable, right? Because the x limit would go to you would have to evaluate the x limit using 1 minus y square by b square into a square, right? So that would be the x limit, and then the y limit would be from minus b to b. But if you use this change of coordinate, then you can see that the integral gets simplified. And the limits for these theta and r can be figured out from this, because x varies from the extreme position is minus a to a, and y varies from minus b to b, and then you can see that the corresponding limits for r and theta are 0 to 2 pi and 0 to 1. Okay, so that's so that you can figure out for yourself, and then finally if you evaluate this, you will get that this is equal to pi g alpha a cube b cube divided by a square plus b square. Okay, so from this now we will get the torsional rigidity. So do that. So what we will get is the d now, that is the torsional rigidity. Torsional rigidity is b is equal to t pi alpha, that is equal to pi g a cube b cube divided by a square plus b square. So this is a cube and this is b cube here. So one of the things you should always verify is that whether so suppose whenever you are deducing a more general result, you should always try to see whether your result reduces to some known result, right, from whatever we have derived previously. So in this particular case, the circle is a special case of the ellipse, right? So if you are generalizing the result to an ellipse, you should check that under the special case where a is equal to b, our results do reduce to that of a circle. This is a check that you should always carry out, because there could be some calculation error or some error that you may have made, and that will come out, right, if you do this, if you carry out this particular check. So here if we put, so if a is equal to b, right, a is equal to b, then you will get that d is equal to g times pi. So this will go to a to the 6, and this will go to 2 times a square. So it will go to g times pi a raised to 4 divided by 2, which is equal to g times v, right? So this is exactly the torsion rigidity of a circular shaft, and so this result does reduce to that for a circular shaft as expected here. So, so you can see that now we are able to find the entire stress distribution by using this Prandtl stress function. But in order to find the displacements, we still need to find the warping function, right? Because we have seen that this uz is equal to alpha times psi of x comma 1. Right? So this, so we need this warping function in order to find this component uz. And so one way to find the warping function would be to use the relation between g and phi. So you can use g as equal to half of x square plus y square plus phi by 2g alpha. So we can use this particular relation, or and then you can find the warping function using the Cauchy-Riemann equation. So that is one way to do it, or we will follow another way here. So that is we can just try to find the complex valued function of which psi and g are the real and the imaginary parts. So that also approach I had indicated in the last time. So we will now demonstrate that particular approach here. So let's guess, in this case again, W of z is equal to psi plus ig is equal to I times c z square plus k. So where the c and k are constants to be determined here, and this z is equal to x plus iy. Z is equal to x plus iy, and c and k are constants to be determined. So let us do that. Okay, so what we'll get is that we'll get so if you expand this out, and we will use the fact that so in order to determine these constants, we will use the fact that g is equal to half of x square plus y square on c. So find c, k using this particular factor, right? And so what you will get is that you will get psi. You will get that psi is equal to minus 2xy times c, and g is equal to x square minus y square times c plus k. Okay, now you write that this is equal to half of x square plus y square on the boundary, and then you and plus the fact that x square, so this is equal to half of x square plus y square, on c, where the equation is x square by a square plus y square by b square is equal to 1. So you need to substitute this x square is equal to 1 minus y square by b square into the whole thing into a square, and then you will see you can find the constants. And so the constants will turn out to be c is equal to a square minus b square divided by 2 times a square plus b square, and k is equal to a square b square divided by a square plus b square. So from this we will get that psi is equal to minus of a square minus b square times xy divided by a square plus b square, and the conjugate function g is equal to a square minus b square times x square minus y square divided by 2 times a square plus b square plus a square b square divided by a square plus b square. So this is the expression that you get. Now, as I said, this g expression would have also been obtained from the phi expression, right? I already mentioned that. So that is using that expression half of x square plus a square plus phi divided by 2g alpha. You can use that particular expression also in order to find this expression for g. So we could have found out, so that was the other approach, we could have found out g from phi and then use the Cauchy-Riemann equations to find out what size. But I mean, whichever way, any of these approaches is fine here. Right, and then okay, so now we can find out what is the displacement field. So you will get that your ux is equal to minus alpha yz, your uy is equal to alpha xz, and uz is equal to minus of a square minus b square times alpha times xy divided by a square plus b square. So this is now the expression for this uz. So uz is the displacement of this particular face coming out of the board, right? So that is the z direction is this particular direction here. So now you can see that again, so as usual, we should first verify whether our results reduce to that for a circle, right? And so for a circle, you will get that a is equal to b, and you will see that the warping function goes to 0 as expected, right? We have already discussed this, that the warping for a circular cylinder is 0, right? Because each cross section just rotates in its own plane. There is no displacement in the out of plane direction here. But now, if you take that a is greater than b, let us say, then you will see that this quantity in the first quadrant will be negative, right? So here you will get a negative displacement. Then in this quadrant you will get a positive. In this quadrant you will get a negative, and in this quadrant you will get a positive displacement. So basically, if you are twisting the cylinder in this particular way, then the points which are on this in this first quadrant, they will go into the board. The points which are in the second quadrant, they come out of the board. Then the points in the third quadrant go into the board. The points in the fourth quadrant come outside the board, right? So, and there is a switch along the symmetry axis. So you can see that along the symmetry axis, the warping function has to be 0, right? Because it's a symmetry axis, right? And so it can neither go up or down, right? Because if it goes up, then there is a bias, correct, towards the positive direction. But because it is a symmetry axis, there can be no bias either towards the positive or the negative side. So always on the symmetry axis, so you have to remember this, on the symmetry axis, your warping function is always going to be 0. That's already another check on your results, that whatever you are computing. So here you can see that the x equal to 0, which is the y-axis, and the y equal to 0, which is the x-axis, these are the symmetry axis for this particular cross section. And you can see that the warping function is equal to 0 on those particular axes. So basically it goes from negative to positive, but along this particular line here, the warping function is 0. Then similarly along this particular line, the warping function is 0, but it goes from positive to negative, it passes through 0. Similarly from negative to positive, it passes through 0, and then from positive to negative, again it passes through 0. So, so it's a very interesting pattern that is formed for the displacements, using this analysis that we have here. Right, and so, okay, so let us move ahead on this. So in your, you will be able to solve similar problems. So in the assignment problems, you will solve an equilateral triangle and then a circular shaft with a cutout. So I will just mention that particular problem said, that is part of their homework problem, but I will just briefly mention the results for a circular cutout, because it's a very important problem from a practical viewpoint, because you will have keyways, right? In a rotating shaft, there will be some gear or something that is mounted on the shaft, and that is connected to the shaft through a keyway, right? And so the moment you cut a keyway, and then the shaft is subjected to a torque, then there are stress concentrations that are induced in the shaft. And so this particular problem of a groove in a shaft gives you an idea about such stress concentrations, and so you will see that the stress concentrations are indeed quite high. So this is the geometry. So this is a groove here, circular, and then this is the axis. So this and radius is B, and this radius here is A. So the radius of the shaft is A, and the radius of the groove that is cut out from this is B. And if you now find out, so the W of Z for this particular cross section is I times AZ minus AB square by Z plus B square divided by 2. So this is what the result comes out. And so I'll just talk about the maximum shearing stress. So you will get that T max in this particular case, T max is equal to G alpha times 2A minus B. So this is the result that you get, and it occurs at this particular point here. So let's call this point as A. So this maximum shearing stress occurs at this particular point. So and at this particular point, the shearing stress is 0. So you can see that if now B is much smaller than A, so for B much smaller than A, T max is approximately 2 times G alpha times A. Correct? And so you can see that if suppose this groove had not been present, then it would have been just G alpha A. But now because of the presence of the groove, there is a stress concentration factor of 2. So this is a very important point, that even if you consider an infinitesimally small groove, even then there will be a stress concentration of 2. So this is something that I was mentioning last time, that you cannot simply take the limit as B tends to 0 and get the result for the solid shaft. Okay, so the moment you have even a very small groove, you will get a stress concentration. So this so we can say here, so the maximum shearing stress is almost doubled. Due to the presence of a groove. Due to the presence of a small groove. And so the practical application I have already mentioned, that if you have a circular shaft, you will have a keyway in that, and so this is like a keyway, and then you will get very sharp stress concentrations in the keyways, right? And so so this kind of an example gives you an idea about such stress concentrations here. So actually one thing to note here is that suppose if you have a, so this is a concave groove, but suppose if I now introduce a groove like this, I mean in the sense, or an, if I add material now to this particular shaft, then actually here the stresses will be very low. It's only when you cut out a portion of the shaft, then the stresses go up. But here the effect is not much. If you add material like this, like a convexity, if If you add a convexity to this shaft, then actually the stress concentration is normal. But if you remove material, then actually the stresses go up. So these are some of the things that come out of such analysis here. So now you will appreciate why mathematical analysis is important, because it gives you an idea about how to design a system in an actual practical situation here. Fine. Now let us look at another interesting example, which is that of a rectangular cross section. So here, so this is what I was saying, that here you cannot use just the equation of the boundary multiplied by a constant, right? So, cannot use phi equal to m times x square minus a square by 4 times y square minus b square by 4. You cannot use this. Just the trick that we use for the elliptical cross section, we cannot do that. So this does not work, because you will not get del square phi is equal to a constant. We need del square phi to be minus 2g alpha. So if you take this to be the equation of the to be the equation for the Prandtl stress function, then you will not get del square phi to be a constant. And so we have to follow some other approach here. And so actually this is a very nice example to introduce Fourier series kind of solution here. Okay, so let us now find the solution by writing the equation for the conjugate function here. So we will write now g as equal to c plus k times y square minus x square plus summation of n is equal to 1 to infinity of a n cos alpha n x times cosine hyperbolic of alpha n times y, where alpha n is equal to 2n minus 1 times 5 divided by 8. Okay, now, so first of all, what we have done here is that you will see that we have combined three types of harmonic functions here, right? So C is a harmonic function, y square minus x square is also a harmonic function, and cosine alpha n x, cosine hyperbolic alpha n y is also a harmonic function. So basically we have superposed a combination of harmonic functions in order to solve this particular problem. Now, it is also true that suppose if you took sine of alpha n x and sine hyperbolic of alpha n y, that would also be a harmonic function. But remember that we need to satisfy the symmetry conditions, right? That on x equal to 0 and y equal to 0, your warping function should vanish. So if you take the conjugate function of this, that means the warping function associated with this, you would get sine alpha n x and sine hyperbolic alpha n y, right, for the warping function. And then you can see that vanishes on the symmetry axis. So satisfying the symmetry conditions is also important, and so this is the correct combination that you have to follow. So no other combination will work to give you that the warping function is 0 on the symmetry axis here, right? And similar things here also. So the function conjugate to this would be xy, correct? And so that vanishes on the symmetry axis, and so on. So we will find that at a later stage, the warping function, but right now we will go with this particular thing. And this choice now, 2n minus 1 pi by 8 is dictated again by trying to satisfy the boundary condition. So we will see that if you take the corresponding phi function, right, that has to vanish on this particular edge, or alternatively g should be equal to half of x square plus y square on this particular boundary. So what we are doing here is that we are choosing the alpha n such that this whole part vanishes on this particular edge here. Okay, and then we will use the fact that g is equal to half of x square plus y square to find c and k on this using the condition that g is equal to half of x square plus y square on this particular boundary. And then we will find the constants a n by using the fact that g is equal to half of x square plus y square on the top and the bottom boundary. So let us go through this whole procedure. So on x equal to plus minus a by 2, we will get that half of a square by 4 plus y square is equal to c plus k times y square minus a square by 4. Okay? And this has to be valid for all y, correct? And so we can match the coefficients of y square and the constant, and then actually these are two equations, because as I said, the functions constant and y square are linearly independent functions, and so we can match the coefficients of y square and the constant term, and then from that we can get two equations for the two unknowns c and k. So what you will get is that c is equal to a square by 4 and k is equal to 1 by 2. So because this part is not playing any role, because we have chosen the alpha n such that that is equal to 0 on the edges, x equal to minus a by 2 and x equal to plus a by 2. Okay. Then once we find out this c and k, then now we use the other edge. So on the other edge, so that is y equal to plus minus b by 2, you will get that x square minus a square by 4 is equal to summation of a n times cos of alpha n x times cos hyperbolic of alpha n b by 2. Okay. And now we need to find out what these constants a n are. So this is running from n is equal to 1 to infinity here. So we use the orthogonality of the cosine functions in order to find. So you must have seen this when you studied your Fourier series, right? So this is just exactly like a Fourier series, because this part is just a constant, okay? So that can be even clubbed into an. You can call that as bn, let us say. So it is this summation is of the form bn cos alpha n x, and so you can find out these coefficients bn by using the orthogonality of the cosine functions here. So so basically you are multiplying this whole thing. You can think about this, that you are multiplying this by cosine of alpha m, okay, where alpha m would be alpha m is equal to 2m minus 1 pi divided by 8, and then you are integrating this. So you are integrating it between the limits x equal to minus a by 2 to plus a by 2, and so now this function is orthogonal to this function over the interval minus a by 2 to a by 2, right? So minus a by 2 to a by 2 of cos of alpha n x cos of alpha n x dx is equal to 0 if m not equal to n, right? So you are using this orthogonality of the cosine functions in order to find this. So basically, so you can imagine now you take suppose n is 10, let us say, just for the sake of an example. Then for n equal to 1, you will get 0, because the integral of cos x cos alpha 10 x is equal to 0. Then next time n is equal to 2, so again the integral of this will be 0. So it will be non-zero only when n is equal to 10, correct? And so in that particular case you will get a non-zero value. That value will be just a by 2, correct? And so that integral can be found out, and so you will get a of m. And similarly, now you keep on varying m from 1, 2, 3, 4 up to infinity, and so you can recover all the m's here. So I will just give the final result here. So what you will get is that an is equal to 8 times minus 1 raised to n times a square divided by 2n minus 1 times pi cube times cosine hyperbolic of alpha n b by 2. So this is the final result that you will get. Okay, so by using the orthogonality of the cosine functions here. And so now the problem is solved because we have been able to find out what is this c, what is this k, and what is this n. So let us now find out the corresponding xi and phi functions, which is the primary stress function here now. So corresponding to this g, you will get that xi is equal to xy plus summation n is equal to 1 to infinity of an times sine alpha nx times sine hyperbolic alpha n times 1. So this is what I was saying, that your warping function should vanish on the symmetry axis. So at x equal to 0 and y equal to 0, you will see that the warping function is vanishing, right? And so this is the correct warping function corresponding to this. So this is found from this using the Cauchy-Riemann equations, right? And so and then the primary stress function phi, that can be found out directly from g. So that is g alpha times a square by 4 minus x square plus summation n is equal to 1 to infinity of an times cos of alpha n x cosine hyperbolic of alpha n times y. So you can verify that phi is now equal to 0 on this particular boundary. So phi is equal to 0 on the entire boundary. So you can verify that. So again, the orthogonality of the cosine functions will play a role. So you can see that at least for x equal to plus minus a by 2, directly it is 0. And then for y equal to plus minus b by 2, you will have to use the orthogonality in order to show that this whole thing vanishes of all this one here. Then what about the maximum shearing stress? Okay, so let us look at that now. So the maximum shearing stress, T max, let us see where that occurs. So T max in this case is equal to tau yz at a by 2 comma 0. So assuming that your a is smaller than the b, basically it is occurring along this one, and then the tau yz, so this component, because this component is just going to be 0, the tau xz component is just 0 because it's a traction free boundary. So only the tau yz component along this is going to contribute to this T max, and so that is equal to g alpha times a plus summation n is equal to 1 to infinity of a n alpha n sine of alpha n a divided by 2. So this is the maximum shearing stress, and one can also find out what is the torsional rigidity corresponding to this. So you will get that d, which is equal to t by alpha. So for this you need to carry out the integration. Okay, so the t is equal to 2 times integral of phi dA. So one can integrate this function phi, whatever is shown here. You have to integrate that from between the limits for x as minus a by 2 to a by 2 and minus b by 2 to b by 2 in this particular case. And so the torsional rigidity will be g times a cube b divided by 3 minus 64 divided by a times summation n is equal to 1 to infinity of 1 by alpha n raised to 5 tan hyperbolic of alpha n b divided by 8. So this is the expression that you get for the torsion rigidity here. Okay, then what does the warping pattern look like in this particular case? So that's also very interesting. So let us draw what the warping function looks like in this particular case here. So this is the warping function. So if you plot this warping function, then let us see how it looks like. Okay. So suppose if I take a square cross section. Okay. So this is a so these diagonals will be also the symmetry axis here in this particular case. So you will get now. So this will be negative. This will be positive. This will be negative. This will be positive. This will be negative. This will be positive. This will be negative, and this will be positive. So this is a square cross section. Square cross section. So basically again the warping function has to be 0 on each of these particular lines because these are all symmetry lines here, and so it crosses over from negative to positive, but it is 0 along this particular line. Then again it crosses from positive to negative. It is 0 along this particular line. It crosses from negative to positive. It is 0 along this particular line, and so on. So basically here negative means that it is going into the board. So the all the displacements here are into the board. Then this part comes out, so it bulges out. Then this part bulges in. This part comes out. Then again this part goes in. This part comes out, and so on. So this is the warping pattern that you get for this particular example here. So as you can see, this is a very interesting warping pattern, and then again we have to satisfy the condition that it has to go to 0 on the symmetry axis here. Now one other point that I would like to mention here is that see, we took a function that was cosine in x and a cos hyperbolic in y. It is also possible to have a cosine hyperbolic in x and a cos in y. So that is also another possibility. So what we have to remember is that the form of the solution need not be unique. Okay, but the final value that you are computing will be unique. So this is something very important. When you have an infinite series, it is possible to get two different forms of the solution. So forms means they will look different. So let me just give that as an example here. So you could also have got, so G is equal to C plus K times y square minus x square plus summation of a n cosine hyperbolic alpha n x and cosine of alpha n y. Also, this is also a possibility. Because in that particular case, you will choose the alpha n such that it vanishes on y equal to plus minus b. So we took the choice as 2n minus 1 pi by 8. So in this particular case, you will choose your alpha n to be equal to 2n minus 1 pi by b in this particular case, because we want it to vanish on now the edges y equal to plus minus b. And then you would again use the orthogonality of the cosine functions in order to find out what the constants a and r by using these two edges. Okay, so you can see that this form now looks a bit different than the form that we had earlier. But as I said, that finally when you find the value of this entire thing at a given point, you will get the same solution. Okay, so that is one important thing. Also in the book you will see that it is also possible to find a solution for phi using a double Fourier series instead of a, so here this is a single Fourier series. It is also possible to use a double Fourier series, and it is and one can find a solution using that also. But this method is preferable because the finding the warping function and the conjugate function is easier when you use a single Fourier series, whatever I have shown you, instead of the double Fourier series. So you need not follow the double Fourier series approach. You can just follow this particular approach. But the important point is that although the form may look different, but finally you have a unique solution, because we have already shown that the solution for linear elasticity is going to be unique, and so this will finally give a unique solution, even though you may start out with different forms for the solution here. Okay, stop here.